Hello, I'm Charlie Thompson, and in this video we're going to talk about processes that lift air, mid-latitude cyclones, which are the source of all of the rain pretty much that we get in the wintertime, and then I'll briefly talk about weather forecasting. So first we're going to talk about processes that lift air. Lifting air is very important because if you want to make it rain, you need to lift air up. There are four mechanisms that are responsible for lifting air: convergent, convectional, orographic, and frontal. So let's look at each of these in turn. Convergent lifting occurs when air converges or comes together around a center of low pressure. So in this case, there's warm air, it's rising, and the rising air creates an area of low pressure, which brings more air into it. Here along the ITCZ, this is a great example of convergence. You've got the northeast trade winds, the southeast trade winds coming together along the ITCZ, and the air, when it comes together, coming in from the north, coming in from the south, can't go down. The only place for it to go is up. So it rises in the troposphere and then spreads out and sinks, making the subtropical high, flows back to the equator, rises, sinks, makes the subtropical high, flows back to the equator. So in this region, there's lots and lots and lots of convergent lifting. The next is convectional lifting. Convectional lifting is very straightforward. Sun shines on ground, ground gets warm, warm air rises because it's less dense. So in this case, there's a plowed field, so it's dark, so the albedo would be low. There's also moisture. So the combination of both of those, a dark surface, sunlight, and water vapor, you're going to get condensation. As the water vapor condenses, it releases heat. The air keeps rising. So here's a picture of convection over Florida. There's some sort of tropical storm. You can see the air swirling counterclockwise into an area of low pressure. Little cumulus, these are all little cumulus clouds, little popcorn clouds. These down here in South Florida look like they're developing, especially that one, looks like they're developing into cumulonimbus clouds. And here's another image of Florida showing the same thing. In this one, the contrast is a little bit better. The land-water heating differences. Sun shines on the land gets warm, so air rises, which then pulls in more warm, moist air off the ocean, which then rises, expands, and you've got a positive feedback loop. You can see Lake Okeechobee, that clear spot right there, is another great example of land-water heating differences. In fact, you can see there's no clouds there. There's a little tiny lake there, big lake there, big ocean. Orographic lifting is the most consistent of all of the lifting mechanisms. We've talked about orographic lifting before in the context of upslope fog. We've talked about orographic lifting in the context of lenticular clouds. And here's orographic lifting just as a lifting mechanism. So it's pretty simple. To make orographic lifting, all you need is wind and a mountain. So as the air runs into the mountain, it gets lifted up. As the air rises, it expands and cools. At some point, it hits the lifting condensation level. As it keeps rising, it keeps cooling. As it keeps cooling, you get more and more condensation. And then as soon as you run out of mountain, the air won't be forced aloft anymore. So the lifting stops, so the cooling stops, so the rain stops. On the other side of the mountain, if conditions are stable, the air will sink, but in any event, it's not going to rise anymore, so you don't get any more cooling, you don't get any more condensation, you don't get any more rain. As the air sinks, it'll heat up, and it'll get compressed, and it'll dry out, and so you have these usually warm winds blowing down slope. We've talked about these in the Santa Ana winds in Southern California. We've talked about it in terms of the Diablo winds in the Bay Area. In the Pacific Northwest, they're called Chinook winds. They're also called snow eaters because the air as it sinks gets dry, gets hot, and so if there's snow, the combination of hot, dry air is going to melt it really quickly. And on the other side, on the inland side of the rainy part, is called the rain shadow. So this would be like Reno, Nevada. As soon as you're going In fact, many of you have seen the results of orographic lifting as you drive out of Sacramento up towards Donner's Summit. It gets colder. We have oak trees down in Sacramento, and then you have pine trees, you have fir trees. Then as soon as you get to Donner's Summit, the pine trees drop away and you have scrubby bushes, and that's because you're in the rain shadow. Orographic lifting, one more time, is the most consistent of all the lifting mechanisms because it doesn't depend on stability. All the other lifting mechanisms, convergent, convectional, and frontal, depend on temperature differences of two different air masses, or the temperature difference between the air that's next to the ground and the air that's around it. So there's some sort of temperature difference resulting in air rising, but with orographic lifting, you just need a mountain. Washington State has some excellent examples over here. This is a Google image, Google Maps, Google Earth image. You can see Mount Rainier, and Mount Rainier is getting 162 inches of rain. This is what Mount Rainier looks like. On the other side, there's Yakima in the rain shadow. In fact, you can see this dotted white line is the crest of the Cascades. So on this side, on the east side, it's in the rain shadow, and you can see it's brown. Here's Yakima. They get about 8 inches of rain. Mount Waialeale gets about 486 inches of rain. It is, in fact, the rainiest spot on Earth on average. And on the rain shadow, they get about 20 inches of rain. So here we have a Google Street View image of the wet side on Kauai by Mount Waialeale. You can see it's very lush, lots of ferns. And then on the rain shadow side, it's pretty scrubby, pretty dry. California, we have the same pattern. In California, there's two patterns that determine our precipitation. One of them is air pressure. So down in Southern California, there's the subtropical high. As you go north, you're getting more under the influence of the polar front, and so there's more and more rain. But really, the driver of rain in California is going to be altitude or elevation. The higher elevation, in fact, you can see over here on this side, this is rainfall, so we're getting lots of rain. We're getting very little rain. Then this is showing elevation above sea level. Here's the Central Valley. You can see the Sutter Buttes. Here we have the Sierra Nevada. We have going up into the Cascades. So on the other side of the Sierras is a really impressive rain shadow, which explains why Nevada and inland Southern California is so dry. An interesting thing to think about is that 30 million years ago, the Sierra Nevadas hadn't been lifted up. They wouldn't have been at the current elevation. So a lot of the rain that's falling in the Sierras would have fallen across Nevada. So the Sierras would have been drier, Nevada would have been wetter. Just something to think about. Frontal lifting is the mechanism where a warm body of air moves into a cold body of air, making a warm front, where a warm air mass moves into a cold air mass. The warm air, because it's less dense, moves up and over the cold air. Warm fronts are about 1,000 kilometers wide. They move about 25 kilometers an hour. Here's an image of a warm front moving along at 25 kilometers an hour. The warm, moist air gets lifted up on top of the colder air. And with a warm front, and this is why I made such a big deal out of cirrus and cirrostratus clouds, the pattern of clouds, when a warm front moves in, goes from cirrus to cirrostratus. The clouds get lower, altostratus, get lower stratus. Then when a warm front moves through California, we usually get nimbostratus clouds. Over the course of a day or so, we'd see high clouds, wispy clouds, and the clouds get lower and lower and lower, and then it rains. With us, the warm front comes right after the warm front. There's a cold front. Usually they go together, and I'll talk about that in the context of mid-latitude cyclones, why we get the warm front with the cold front. With a cold front, the cold air mass is moving under, pushing up, lifting the warm air mass. Cold air always lifts warm air. Cold fronts are about 400 kilometers wide. They travel about 40 kilometers an hour, so they're narrow and fast. So here we have the body of cold air moving along the ground, lifting up the warm air. So here we have the cold air mass Maritime polar, for example, moving along the ground, lifting up the warm air. Maritime tropical, for example, creating heavy, brief rain because the cold front moves faster, and you can see the leading edge here is much steeper than the warm front. The air gets lifted much faster, so you get heavy rain, but just for a little bit. So I've included in the notes for you to look at this animation of a cold front. In fact, I'm going to skip it and play it out of order. I don't want your cold front. I want a warm front. So the warm front, the air is moving along this maritime tropical air mass, and it gradually gets lifted up by this colder, denser air. And it gradually pushes it out of the way, but the cold air is more dense. So the warm air moves more slowly. The warm front moves more slowly than a cold front. In this case, it's a warm front. I'm going to back it up so that we can take a look at a cold front moving along. As I mentioned, with the cold front, it's going to move quickly. This would be maritime polar air lifting up maritime tropical air. As it lifts it up, the air rises, you get really heavy rain. And usually, if you think about it, this is often the way our storms go, that we'll get really heavy rain very briefly at the end of a storm. And then what's behind that, of course, is this cold, dry air. Because this air is cold, it lifted up the warm air, but then the next morning when you go outside, it's usually clear and blue skies. And cold, because this is the cold front moving in. Here we have a view from space of a cold front moving along, lifting up. All embedded in here would be lots of cumulonimbus clouds, lots of thunder clouds. We usually don't get thunder clouds in Sacramento because by the time we get our storms, there's not enough energy to create really good thunderstorms. There's not enough water vapor. The storms aren't warm enough. There's not enough water vapor, so there's not enough energy to create thunderstorms. That's just a really great picture of a storm someplace on the plains. Probably tornadoes are spawning someplace. Now we're going to talk about mid-latitude cyclones. Mid-latitude refers to the latitude that they occur at. They're not in the tropics. They're not tropical cyclones. That will be one of the very last things we talk about in this chapter. It would be violent weather. Mid-latitude means that it's in the mid-latitudes, and cyclone means that there's just air flowing into an area of low pressure. Sometimes mid-latitude cyclones are called wave cyclones. Sometimes they're called extratropical cyclones. We'll just call them mid-latitude cyclones. So you have a warm front and a cold front spinning around a center of low pressure. Mid-latitude cyclones are caused by the conflict between the warm air mass and the cold air mass. I think of it in terms of mythology that you can't have a hero without a villain. And so it's the conflict between these two air masses that creates the storm. Here is a satellite image with some annotations showing the two different air masses usually involved with a mid-latitude cyclone. There's warm, moist air coming out of the tropics. As this air comes up out of the south, it collides with cold air, lifts up, making a warm front. There's a center of low pressure right, in fact, in this picture, the low pressure looks like it's right in there. So the cold air is spiraling out of the Arctic, moving along counterclockwise because it's in the northern hemisphere. The whole system rotates counterclockwise. This warm air comes up counterclockwise. This cold air is coming in counterclockwise. This cold air is coming in counterclockwise. But then this cold air is going to move along and lift up this warm air, making a cold front. So here we have a cold front. Here we have a warm front. And over here we have an occluded front, which I'll talk about in a minute. This is an image of a cold front and a warm front taken by NASA. There's a nice area of high pressure in here. We'll take a look at that later. This is actually the same mid-latitude cyclone that I sent you. I posted to the announcements. I said, hey, here's a good picture of a mid-latitude cyclone from NASA. You should go check it out. So, and then up here you can even see, I can see it on my monitor. Maybe you'd have to blow it up. But these look like really wispy cirrus clouds. And that's, again, an indication that a front's moving in, those cirrus clouds. And here you can actually see them. Cirrus clouds, you can see cumulus clouds. They're small because the conditions are stable. Along here, you've got a string of cumulonimbus clouds because conditions are unstable. And then over here would just be stratus and nimbostratus clouds. So let's take a look at this one. So this is from March 15th of this year of 2020. And here we've got a mid-latitude cyclone. Let me just hit refresh. So here we've got a mid-latitude cyclone. You can see the air is rotating counter. This right in here is the mid-latitude cyclone. Here is one front. That would be the cold front. And then over here is the warm front. Warm fronts are harder to see, but you can see that there's a difference in the direction of the air. In fact, if I zoom in a little bit more, you can see that the air here is flowing out of the south. This would be warm air flowing up, and then it's running into cold air, making a warm front up here. You've got cold air flowing down that's then lifting up this warm air, making a cold front. So if I turn on the clouds, you can see a little bit better that cold front. Warm fronts often are blobby and weird looking. They don't. Cold fronts, I think, always look like they're diagrams. You've got the cold air moving along. Here's the warm air. You've got a band. It's narrow. Here's another cold front over here. But the warm fronts are usually much wider and less distinct. And that's the amount of water in clouds. This is water vapor, and I thought it would be nice to give you an example of water vapor from the tropics moving up to the mid-latitudes. This air is very, very dry. It's brown, and on the color scheme, brown is dry. Light blue is the moist air. So here we've got the cold front. Here we've got a warm front. And now let's take a look at another mid-latitude cyclone. Okay, so here's another example of a mid-latitude cyclone. I'm going to zoom in again. This one, you can see it's in the Gulf of Alaska. So we've got cold polar air moving along here. We've got warm tropical air moving up. So there should be a warm front in here, should be a nice extended cold front down there. If we turn on the total cloud water, indeed, there's our cold front, there's our warm front. If we turn on total precipitable water, again, you can see it's drawing moisture out of the tropics up to the mid-latitudes. When that water vapor gets taken from the tropics, it's transporting heat energy in the form of latent heat. When that water vapor comes to the mid-latitudes and condenses, it releases heat, which warms the air. So again, just a reminder, the transport of water vapor is actually a transport of latent heat energy. So let's go back to lecture now. And I've included a bunch of examples of mid-latitude cyclones for you in earth.nullschool.net. So if you just click on those, it should open up a page that'll take you through to earth.nullschool.net. I would really recommend playing around with the controls. You could turn on air pressure, you can turn on relative humidity, you can turn on the amount of water, you can have it display the amount of water in the atmosphere, the specific humidity, you can have it display relative humidity, you can have it display temperature. And here's an animation that I've included for you. Again, it's by Pearson. And what we've got is a mid-latitude cyclone working its way across the United States over the course of a couple days. Here we're seeing it again. You've got the warm air moving up. You've got cold air coming down. This is an occluded front, and I'll explain that in a minute. I think it'll make more sense. I'm just going to keep playing that. And eventually they'll show it to us. So this is an animation of a mid-latitude cyclone. It's embedded in the notes, so you can watch it. You can turn on the narration. You can see here we've got the cold front. Here we have a warm front. I mentioned warm fronts move about 25 kilometers an hour. Cold fronts move about 40 kilometers an hour. This would be maritime polar air pushing along. This would be maritime tropical air coming up. And eventually the cold front catches the warm front, and it's going to lift all that warm air up. And when that happens, you get what's called an occluded front. So again, the cold front moves faster than the warm front, so the cold front catches up to the warm front, making an occluded front. Typically, these storms take a couple days. And now we've got a side view. This is my favorite part. So this cold air here is this cold air mass here. This is the cold front moving along the ground, lifting up this warm air. This warm air is this in the middle here. And then this warm air here, there's actually warm air here, but it's aloft. So what we're seeing is the temperature of the air on the ground. So this would be cold air, this is cold air, but above it is this warm air. So there's the warm front, here's the cold front, and as they move along, the cold front's going to catch the warm front. And once the cold front catches the warm front, that's called occlusion. And the next thing that happens after occlusion is the whole storm goes away. So I mentioned before, I think of this in mythological terms. And so you've got the contrast between this cold, dry air and this warm, moist air. So when two different air masses meet, they don't mix. They form a boundary layer, a front in between them, because they have different temperature and humidity characteristics. So usually there's warm air on the ground and cold air up above. This air coming off the Gulf of Mexico is warm and moist, and this air is cold and dry. But after you get occlusion, the warm air gets lifted up. And once the warm air gets lifted up, it's going to expand and cool. You'll get condensation and you'll lose water vapor. So the warm air got lifted up and now it's cold. And as it cools, you're going to lose water vapor, so it's going to become drier. This cold air along the ground is going to pick up heat from the sun, so it's going to warm up, and it's also going to pick up water moisture because of all the rain that fell. So the cold, dry air is going to become warm and moist. The warm, moist air is going to become cool and dry, and so they're all the same. There's no conflict anymore. There's no contrast, and so the whole storm just dissolves. However, it'll start again because the tropics are always getting more energy than the poles. This whole system is set up because of the imbalance in energy between the tropics and the poles. So even though the warm air got cold, even though the moist air got dry, and the cold, dry air is now going to be warm and moist, that imbalance between the tropics and the poles is going to start up again. So there's stages to a mid-latitude cyclone. There's cyclogenesis, which means the beginning of the storm. This happens along the polar front as the westerlies move the warm, moist air from the tropics towards the poles, and the polar easterlies sort of push the cold air out of the poles towards the tropics. There's the open stage, when warm air is moving northward, cold air moving southward. Rotation, you get an area of low pressure, and the whole system starts to move counterclockwise. So the animation that we just saw, that would be during rotation. Low pressure has formed, air mass is moving counterclockwise, and then the animation moves into the occluded stage. So it starts in rotation, moves on to occlusion after the cold air catches up to the warm air. And then after that is dissolving, because the warm air is cold, the cold air is warm, there's no more conflict, and the storm just goes away. Here we have a mid-latitude cyclone. Here we have the open stage. Here we have another cyclone. This is in the occluded stage. The two ways of showing an occluded front is either little blue triangles and little red suns. I should probably talk about that. Cold front, the symbol, is little blue triangles, and the teeth are pointing in the direction the front is moving. So in the book, figure 4.34, you can see the little green arrows indicating the direction of the movement of this cold, dry air that's actually making the cold front. And then over here, we've got warm, moist, maritime tropical air pushing up, making a warm front as this warm air gets lifted up and over this cold air. So here we have a cross-section between a cold front and the warm front. And then over here, we have a cross-section of an occluded front. So we have cyclogenesis, open, open, followed by rotation, followed by occlusion, followed by dissolving. In the wintertime, the storm tracks shift south as the subtropical highs and the subsolar point all shift south. So in the summertime, mid-latitude storms are going across Canada. In the wintertime, they drop and go across the United States. Another diagram showing the same thing. I like this. I stole this from another weather book. So you can see the cold front here, warm front here. Here's your cold front, warm front. The same system progressing over 3 days. You have occlusion. Here's a fully occluded front with all the warm air being lifted up. Different weather book showing the same thing. So this could be either one cyclone over 3 days. You can see it's beginning from open and rotation, or rather open, rotation. You're developing that little Oh, they're also called mid-latitude wave cyclones, and the reason they're called that is because in rotation they look like a wave. The top view, the top view along the polar front looks like the side view of a wave. And then over here you have an occluded front, so this storm is on its way out. But they typically take several days, so this could be one cyclone over 3 days. So here'd be Monday, Tuesday, Wednesday. And at any one time, there are several of these mid-latitude cyclones going on along the polar front. Here we have the open stage. You can see, again, the dots on these weather stations, the more colored in it is, the cloudier it is, showing the direction of wind. So here we have, I'll turn on the pointer. Here we have wind coming out of the southwest, wind coming out of the southeast, wind coming out of the northeast. And one of the important things is once a front moves through, the wind is going to rotate 90 degrees. So here you can see the wind coming out of the southwest, and then right here, the wind is coming out of the northwest. So the wind has shifted 90 degrees clockwise. Over here, the wind is coming out of the southeast. Here it's coming out of the southwest, coming out of the southwest. And this is coming out of the southeast. So when the warm front goes through, here it would be cold with wind from the south, and it's cloudy. When the warm front moves through, now we have wind coming out of the southwest, except the wind is going to be warm and moist, at least until the cold front comes through, because driving that cold front is this cold, dry air coming out of the northeast. So as a front moves through, the wind direction is going to shift 90 degrees clockwise. Like here it's coming out of the southeast, coming out of the southwest, and then here it's coming out of the northeast. So this is the open stage, and here we have a weather map showing rotation. You can see the lower the dew point temperature. So again, with these weather stations, the top number is the air temperature. In this case, it's in degrees Fahrenheit. The bottom temperature is the dew point temperature. The closer the two numbers are together, the higher the relative humidity. And the higher the bottom number, the higher the dew point, the higher the specific humidity. So here we've got dew points of 63, 64 degrees. Coming in behind it, this air has dew points of 20 degrees or 10 degrees. So very cold, very dry. The wind here is coming due south. In fact, again, we've got that 90-degree shift, right? Here the wind is coming out of the east. Here the wind's coming from the south. And then right behind it, the wind is coming straight out of the east. So we've got warm, moist air, cool, dry air, and really cold, really dry air driving behind. In fact, in this part, the storm is already, it's not just in rotation, this part is in occlusion. I know that says occlusion. I would think this is a better example of dissolving, so just ignore that word. That part's occluded, but really, it's done. There's no more conflict. All the water vapor, all the latent heat has been expended as that water vapor condensed, so the storm's done. Weather forecasting. Weather forecasting is really very good. Weather forecasting has become increasingly accurate over the years. Some people make jokes about weather forecasters not being accurate, but weather forecasting is incredibly accurate these days, which is impressive given how many moving parts there are. So weather forecasters are looking at air pressure, again, low pressure, rainy, high pressure, clear. Whether it's rising, if it's rising, conditions are going to get clearer. If it's falling, it's going to get cloudier. The temperature, the dew point temperature, how much humidity is present, wind speed and direction, the type of clouds, what types of clouds there are at different elevations, what the current weather is it raining, current sky conditions, including how much coverage there is the sky completely clear, 1/8, 2/8, is it half covered up with clouds, is it completely cloudy? So weather forecasters have to look at all of these different aspects and how they relate to each other in order to make weather forecasts. So they collect lots of weather data. They use weather satellites. Weather satellites tell us where the clouds are. They tell us the temperature of the surface and the temperature of different layers of the atmosphere. They tell us how much water vapor is present. They tell us the relative humidity. They tell us the specific humidity. ASOS, or Automated Surface Observing Systems. AWIPS is the computer workstation that the National Weather Service developed to predict to forecast weather. Doppler radar sends out radio waves and measures how fast they come back. That'll tell us where it's raining, where it's hailing. They can tell us how much rain is falling. They can actually calculate the volume of rain that's falling from the sky. We can track hurricanes. We can track tornadoes. After they develop, we can see tornadoes on Doppler radar. We can also track the migration of birds and bats and insects using Doppler radar. In the weather playlist on YouTube, I put up a couple videos on spotting migrating animals via Doppler radar. It's pretty interesting. So here's an ASOS, the Automated Surface Observing Sensor System. It's got a Doppler radar ball. There's one of these on the bridge over 80, just over by IKEA. Now that I've mentioned it, hopefully you'll see it. There's a rain sensor that measures how much rain is falling, temperature, dew point sensor, a visibility sensor. That way they can give warnings of fog or reduced visibility. A freezing rain sensor, which is really important, especially if we're talking about on a bridge, because the bridge isn't connected to the ground and there's air underneath it and above it. It radiates heat faster than the rest of the roads. So roads on the ground, ice over after the bridges. That's a fun fact. Not something we deal with in Sacramento, but if you lived someplace where we get ice on the ground, you would know that the bridges freeze over first. And by using the freezing rain sensor and the thermometer, they can put up warnings on highway billboards. Here's proof that the government forecasters use desktop computers, which I guess might have been interesting at one point. This is a tornado that destroyed the town of Moore, Oklahoma. You can see that there's this distinctive hook signature, this apostrophe or comma shape that ends right there was the actual tornado itself. So weather forecasters looking at Doppler radar can tell where the tornadoes are after they've formed. They can't really spot them beforehand, but once they start to rotate, they're very easy to pick up, and then they can give warnings and people can take shelter. Here's a link to how Doppler radar can track bird migrations. I hope you enjoy that. Weather maps, some of the things that we can see on a weather map. Well, you should know what this is. Blue line with little spikes in the direction it's moving is a cold front. Little red semicircles like little suns, that's a warm front. Here's an occluded front, so we did an area of low pressure. It's got actual millibars. What else? They're showing a spot, the freezing line, places where it's below freezing. So here we have a cold front, here we have a warm front, maximum temperatures, minimum temperatures, typical weather map. And the next section is going to be violent weather, and that's going to take a while, so I'm going to include that in another video for another day. That's it, and I'll see you with the next video for violent weather.